Hello, it's Keith here, and this is lesson 89 of the platform-specific series of my Z80 assembly programming tutorials. Not quite Z80 today because we're looking at the Game Boy Color, and of course the Game Boy doesn't actually have a Z80 processor. It has a processor based on the 8080 with some Z80-like features, so it's going to make interrupt a little bit different. Usually we would use interrupt mode 1, which will cause an execution to memory address 0038. That memory address does have an OST at it, but that OST is never actually called by any interrupt handler. So we're going to use the Game Boy's own custom interrupt handler for VBlank, which fortunately is pretty convenient. And we're also going to discuss my Chibi Pro ChibiTracks on the Game Boy. So let's go over to our source code and let's take a look at what we've got today. Okay, so here's the file we're looking at today. So this is the example. And so basically, the interrupt handlers don't use the OSTs. What they do is they use a sequence of addresses following that. And so you can see we've got one for VBlank, LCD stat, timer, serial, joypad. The only one we're interested in is VBlank. So this is at memory address 0040. And all we've put at that address, there's only 8 bytes there. So all we've put is a jump to our interrupt handler for VBlank. And all this example does is it actually plays the sound. Now, that's how we put our interrupt handler in the right place in memory, but we still need to enable the interrupt because by default, that interrupt wouldn't do anything, and so we would get no sound. The interrupts are actually controlled by memory address FFFF. There's a memory mapped hardware port there, and basically each of the bits is selecting a different interrupt to enable here. So we want the VBlank interrupt, which is bit 0. So we're just setting that to 1 and writing that to that port there, and that will enable the interrupt. It will allow that VBlank interrupt to occur. None of the other interrupts will occur. So that's how we actually get our interrupt handling. We've used them before for hardware sprites as well, because you can't write hardware sprites outside of VBlank, so you can use the DMA to do that. But in this case, we are using it to update the sound. So let's just take a quick peek at our interrupt handler if I can actually find it. Okay, so here is the interrupt handler for the ChibiTracks software. So there's the play update for ChibiTracks. That will update the sound. Now, the interrupt handler on the Game Boy actually needs a ret-i command. Now, the usual Z80 would only use a ret. We would enable interrupts, then we would return rather than using ret-i. But on the Game Boy, we actually want to use ret-i to return. Now, the Game Boy, of course, has no shadow registers, so we can't use them. So we're just pushing all of our registers onto the stack and popping them all off the stack. The ChibiTracks software uses AF, BC, DE, HL, and it also is supposed to use the IX register, but that register does not exist on the Game Boy. Now, what I've done is I've simulated the missing functionality of the Z80. ChibiTracks is available for Z80, 6502 and 68000, but the GB Z80 version is using Z80 simulation macros. So we're basically using memory addresses to simulate the missing registers, and so we're backing those up by transferring the IX pair to H and L and pushing them onto the stack and popping them back. That's because these are also used in the Mintile graphics routines that were drawing the test graphics there. So that's how we're getting around that. Now, the simulation of the missing Z80 functionality is done by this CPU compatibility script here. There is an alternate version of the ChibiTracks software for the Game Boy. The version here will actually compile to the regular Z80 as well, but for safety as much as anything, I didn't want the ChibiTracks code to be kludged up by lots of these weird macros that were on the Game Boy simulating Z80 functionality, but on the true Z80 were actually just being translated directly to the real Z80 commands. It's not that this would actually run any less efficiently, it's just it looked quite messy because of all of these macros that you would see that were simulating Z80 functionality. I will show you one at the start of the code here. So, for example, that's the LDIR macro because the Game Boy Z80 processor has no LDIR command, and it also has no command to load a pair of registers. The HL pair can't be loaded to the memory address song base, so that is the equivalent of LD song base, HL. So that macro there is just doing that on the Z80 on the Game Boy processor. It's simulating that command. So as I say, the simulation scripts are no slower on the Z80, but they're mighty ugly to look at and confusing. So as I say, I have got 2 versions. Now we need a few different include files for the ChibiTracks software. We need the tweener and fraction 16. Those are for the in-between note calculation. the ChibiTracks software itself here for the Game Boy version here, and Chibi Sound Pro, which is the platform-specific sound driver. This is, of course, going to run the Game Boy version. It automatically switches to the correct version depending on the include scripts. My build scripts will automatically define build GBX and things like that to define which version of the code it needs to assemble. So that's how the program can run on multiple systems. Now, with regards to the Chibi Sound Pro, we do need to allocate some memory. We need about 128 bytes, so we're defining an area for that. Now, the first 64 bytes or so are used by ChibiTracks. There's also some memory used by Chibi Sound Pro, and we're also tagging on the various pointers to the memory addresses that the ChibiTracks software needs for its actual playing of the music files. So we're just tagging those on as well. So basically, we have a few options we can enable. Allow speed change allows the music to be played at different speeds at actual playback time. Now, that might be useful if you've written your music for a 50Hz system and now you're playing on 60Hz, you want to slow it down so it plays at the same speed. Or if you've got a game like Mario where the game music speeds up as the player is running out of time, that will allow you to do that, but it does make the player a little bit bigger and a little bit slower. So you can disable that, and you can multiply the speed in the binary file in the Chibi Tracker software, and you will save some speed. You don't need to enable that function, but I've got it enabled here. Allow relocation is when you export the binary, you specify the memory address it's going to load to. If you disable that and you load it to that address, you don't need relocation. You can disable it and it will load fine. But if you want to load it to a different address, you need to enable allow relocation, and it will recalculate the internal addresses within the song file. I would suggest you leave it enabled. It doesn't take too much memory, and it's saved an awful pain in the backside when it comes to loading the same music file on lots of different systems. Arcos Tracker, the original versions, didn't support that. I think some of the later ones did, but it was a big pain exporting my music files over and over again for different systems because each one had different available memory for loading the music file into. So I would suggest you leave that enabled, but it's up to you. Now, getting the music playing once we've got our interrupt handler ready, there's not too much we need to do. Firstly, we need to enable the sound driver, so we run this init routine, which will do whatever the platform-specific sound driver needs, maybe nothing. And then we're going to load in the address of the song file, song data, so that points to the binary song file, and we're loading that into the memory address song base, which is one of the parameters of the ChibiTracks memory that we defined up here. Now, the other ones will actually be automatically loaded in by the initialization of that song file, which is this start song command. So we run start song whenever we load a new song in memory. So if the song changed when the player had won the level or something, then we would just load in the new address of the song data, and we would run start song again, and it will reset the song, and then it will just keep playing just fine. The actual job of playing and updating the music is all done by this, and this will play whatever song is currently playing. So it's only that initialization that you need to do to get the next song playing, and that's really all there is to it. The interrupt handler is actually fairly straightforward on the Game Boy. We have got some disable interrupt commands within our actual graphics routines because there were some problems with regards to the interrupts were colliding with our graphics routines. Some of our graphics routines, we need to wait for a H or V blank before we write to VRAM, and so I'm disabling the interrupts at the start of the drawing and then re-enabling them at the end of the drawing for safety there. That is going to make things work a lot better. So that is something I'm doing there. But I'd say generally it's pretty straightforward to get the interrupts working on the Game Boy. So as I always say, go to the website, download the source code and the build scripts. You're welcome to use it in anything you can of your own. If it helps you out, go ahead and use it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.